We're going to continue our look at partial derivatives, maybe just do a few more examples, and then start thinking about what these partial derivatives actually mean. Like, what does that really mean when we have these surfaces or these functions of two variables, and it could be more, right? And we'll see that shortly. But what does it really mean when we do these partial derivatives, right? Well, before we answer all those questions, or at the very least attempt to answer those questions, let's address some notational issues, right? Notation is always important because that's how we communicate, right? We communicate all these technical ideas. We need a systematic, consistent way of doing it. So what do we have so far? So let's start. So we have our function f of x, y. We have one notation that's used to represent the first partial derivative with respect to x. So we have our f sub x. It turns out there are lots of other ones. So let me just kind of list a few of them off here. So obviously, if we wanted to, we could add a little bit more detail to this one and just say f of x, and then to indicate that, yes, we will likely end up with another function that will depend on x and y, right? So this is similar to, when you have a function like this of one variable, and whether you write f prime versus f prime of x, right? They're interpreted the same, right? Many times the independent variable is implied. So that this is not much of a change. It's still the f with a subscript, right? But here's another one. Now, so I just wrote this notation, and let me add a little bit more here. So we have the prime notation with this, which is standard. The other one that's notation is our dy dx, right? So what we would like to do as much as possible is to convert this over to kind of fit this new context. And it turns out there is an analogy for this notation, this Leibniz notation, when we go to a function of two or more variables. And this is what it is. But instead of using the d, we use it's actually, I believe it's actually a Hebrew symbol, and you put we call this a partial d, so it's kind of curved over. It's not like straight up. And then you can use either f if you'd like there, and then do the same thing in the denominator, right? To indicate that you're doing a partial derivative of f with respect to x. So you could put this f, or if you wanted to, you could have your z there. That would work as well, right? And then there's some other plays on this. Let me just kind of go back in this direction. If you wanted to, similar to how you could use either f or z here, you can use either f or z in this context as well. So all these mean the same first partial of our function with respect to x. And there's another one that we won't really use it a lot, but I'll mention it just in case you're looking at other resources and you're seeing this stuff out there. What does it mean? Well, again, the process of differentiation starts with the d. In a lot of literature talking about derivatives, they use that uppercase letter d for a derivative, and then now we put the subscript the same way we would put the subscript here to indicate what variable we're differentiating with respect to, and then you can put your f or your z. So I'm just going to put the f there. So these all represent a first partial derivative, right? And use them to your heart's delight, right? So first partial derivative. But again, even that phrase is a little incomplete. I have to state with respect to x now. So I can't throw away the WRT. It has to be foremost anytime we're talking about differentiating a function where you have several independent variables. The question is, which one are you differentiating with respect to? So that always has to be communicated. And then obviously all of these can be translate it over to the first partial with respect to y. I just, everywhere I see an x, I would just change the y. So I'm not going to rewrite the entire list. I'm going to focus on the two notations that we will use the most, right? And it will be this one and this one. Again, with the f and the z are easily interchangeable. So we'll use this a lot, right? And we will use, oh, my partial d doesn't even look like a d. There we go. So there, and then my, these should be y's since I'm doing a partial with respect to y, or indicating what it would look like, right? So then these are the two standard ones that we would use. All the other ones can be used as well, but just, so this is our first, or ways that we will denote our first partial derivative with respect to y. All right. Okay, so let's now jump in and do a few more examples, right? So let's just do a few more examples. Can't get enough examples doing differentiation. So let's start with something like, let's say our f of xy is this function. So let's say it's x squared times y, and then let's say plus x times the tangent of xy, right? And then plus the square root of xy. All right. So there's our function, and let's go ahead and compute the first partial derivative with respect to x, with respect to y, and I'm going to use our Leibniz notation, or what looks like our Leibniz notation, just to get more practice with it. So we have our df. Let's differentiate with respect to x. So there we get to treat all the y's as constant, right? And then we have to make sure that we're applying all our appropriate rules. So for this term, the y is treated as a constant, and it's a constant multiple because it's multiplying our x squared. So I can bring that constant multiple down and multiply the derivative of x squared with respect to x. Now, what I'm going to do, and this is something that we can certainly do mentally, but to kind of emphasize, again, what this notation is referring to, I'm going to add essentially like the conceptual step. So you're going to see exactly what term we're differentiating and which ones we're treating as constant. In other words, it's going to look like this. I will take the partial derivative with respect to x of this x squared, and then I will multiply it by y, right? So again, I'm kind of writing out what we're going to do before we actually do it. And then let's move to the next term. The next term now involves several things that we have to be careful of. The first big thing that we need to realize is that there is a product, and this factor involves x, this factor involves x. So what that means is I have to use my product rule. So I'm going to write down what the product rule says first, and then again we'll actually compute it in the next step. So the product rule says, the way I like to do it, I like to take the partial derivative of the first times the second, so this is the tangent of xy, and then plus the first times now the partial derivative with respect to x of the second, which is our tangent of xy, right? And then we have to do this one. Now, there are different ways you can interpret this. I think the easiest way, and we know anytime we see a radical, in this context, we're going to think of it as something to the power 1/2. But not only that, I can use the properties of radicals and write this as x to the 1/2 times y to the 1/2, right? And then if I do this, I can treat it similarly to how I treated the first term, where I had just an x function times a y function, right? So again, with respect to x, the y to the 1/2 is going to be treated as a constant. So let's do so it's plus, so I'll do the partial derivative with respect to x of x to the 1/2, and then that y to the 1/2 is just going to be brought down, right? So this is kind of, so essentially this is our plan, right? This is our layout or procedure that we're going to carry out right now. But there's still going to be a little twist in it, right? There's still going to be a little twist in it, and that twist is going to come right here. Because when I look at all these partial derivatives that I have to do, this one is pretty straightforward. I'm going to get 2x and then bring down the y. This one is just going to give me 1 times and then bring down the tangent of xy. So plus 1 times the tangent of xy. Here, bring down the x times, but now I have a composite because the xy could be treated as its own function, but then I'm taking the tangent of it. So in addition to the product rule, which we started and we indicated by writing this down, so this is our product rule. In order to compute this partial derivative, we are going to have to use our chain rule. So we need our chain rule here, and keep in mind, right? And keep in mind that we're treating y as a constant. So a lot to process, but again, we can do it systematically. So what does the chain rule say? Take the derivative of the outer. The derivative of tangent is secant squared. And then the chain rule says keep the inner. The inner in this case is xy, so I'm going to bring down that xy. But now I have to multiply by, so I'm going to write this down. I have to take the partial derivative of what's inside, again, with respect to x. But it's another product, x times y, so it ends up being this and then times y, right? Why do we just multiply the y? Because we're treating the y as a constant, and right here it's a constant multiple. So those come down. And then finally, well, not finally, but because we'll have to clean up this at the last step. But again, here using our power rule, differentiating the root, we're going to end up getting 1 over 2 root x. And then I'll switch this back, and then this will be root y. Right? So we're almost done. We just have to finish this one. Now, obviously, when you get better at, treating things as constants and then thinking of, okay, what does it look like for my product or my quotient or my chain or any combination of those, you don't have to write this step, right? This is, again, it's just kind of a mental roadmap to say, okay, this is what we have ahead of us. But now let's conclude this particular journey. So we have, so all of that's pretty good. And then here, this partial derivative of x with respect to x is 1. So usually what I do is I put like the polynomial terms, like the powers of x and y. I usually put those in front, and then the other like transcendental functions, the trig and the e and the ln, I usually put those after, but the order doesn't matter because these are all being multiplied. And then finally plus, and then here what we can do, I can write this as a single fraction as the square root of y over 2 root x. And there we go. So this is the partial derivative, first partial derivative of this function with respect to x, right? Let's see what it looks like if we do with respect to y. This one will be a little bit easier, and here is why. Because in the middle term, only one of these factors has a y. So I don't need the product rule, but I will still need the chain rule. So again, let's write down now what our roadmap to success will be. So differentiating with respect to y, I now get to treat the x squared as a constant. So the x squared will come down, and then I'll do a partial derivative of y with respect to y plus, again, because I get to treat this as a constant and it's a constant multiple, it comes down. So I have x times, and then I will have to do my partial with respect to y of the tangent of xy. And then similarly here, the root x will come down, and then I have to differentiate the root y with respect to y. So I'll write it like this. You'll have the x to the 1/2 times the partial with respect to y of y to the 1/2. And you'll notice I just say, when I say partial, it implies a partial derivative or a first partial derivative, right? All right, so let's see what this one works out to be. So we got x squared. The partial of y with respect to y is 1. So we have times 1 there. And then bring down that x. And again, it has to be the chain rule. Anytime there's a composite, in whatever context, when you have one function evaluated at another function and you're doing a derivative, chain rule, right? And then, so apply so this gives us secant squared. Again, keep the inner, and now we have to multiply by the derivative of the inner with respect to y. But that means I get to treat x as a constant, so then this is x times the partial of y with respect to y. And then plus, again, I'll switch back to the radical, so this is root x, and then this will be 1/2 root y, right? So here's our final answer for our partial with respect to y. So we got x squared and then plus x secant, actually, as I see it, since, everything here is being multiplied, we have an x and another x, so I can just write that as x squared. The y, this goes away, that becomes a 1, so I'm left with x squared times secant squared of xy, and then plus, and then over here I can write this as a single fraction, root x over 2 root y, right? So again, when you on the big picture, you're doing your regular differentiation, but now you just have to make sure that you know what role your variables play. And an extension of this is, so what if you have a function that has more than one variable, independent variable? Suppose you have a function of 3 variables, right? Did I say 1? I should have said 2. But let's say you have something like this, w, and let's say you now have the 3x minus e to the xy over the sine of z plus y squared. So suppose you had something like this, where you had a function w, right, that depends on 3 variables, x, y, and z, and you had to find the first partial derivatives. Well, it turns out then we can either differentiate with respect to x or y or z. So for this type of function, there are 3 possible first partial derivatives. Let's go ahead and compute them all, right? So here I'll use this notation. So w sub x, we're going to take this function, differentiate it with respect to x. And what this means is we get to treat all other variables as constants. So we're going to treat y and z as constants. So let me write that as constants. So like this. So anytime there's a y, we're going to treat it like a constant, but we also have to keep in mind whatever applicable rules of differentiation, we need to apply them. This one, I'm going to treat this as a quotient rule, just so that we see what that looks like, right? We've done the product, we've done the chain, let's do a quotient, just so that no rules feel left out. Let's take the derivative of the top with respect to x, right? So for this term, it's pretty straightforward. It's going to be 3 minus. This requires the chain rule. So when I differentiate my e, I know I always get back the e, and then I have to keep the inner, but then I have to multiply by the derivative of the inner with respect to x. If I differentiate this product with respect to x, the x goes to 1, the y comes down because it's a constant multiple. 1 times y is y. So we have this, right? So that's the derivative of the top with respect to x, and then I have to multiply the bottom. So you notice I'm using my parentheses here because we have lots of terms and we want to make sure that we have the correct order of operation indicated. So this is the derivative of the top times the bottom. Now minus the top, so that's another quantity, 3x minus e to the xy, and then times the derivative of the bottom with respect to x. But look, there is no x in the bottom at all. So this term is treated as a constant. This term is treated as a constant. That means its derivative, the derivative of the denominator, is 0. That's fun. And then this is all over the denominator squared. So I end up with the sine of z plus y squared squared. Right? Well, how does this simplify? It actually simplifies pretty nicely because we have this factor of 0. This term here goes away completely. And then look at what I have left. I have this over this squared. But these two have a common factor. So because this is gone, now I can reduce it. And essentially, I'll use a different color. I can take that and reduce one of the factors in the denominator, so I'll have that to the first power. So it's because of this 0, right? It just cancels or eliminates all of this. My first partial derivative of w with respect to x is 3 minus, I'll put the y in front. I like to put the polynomial terms in front. And then this is all over the sine of z plus y squared. Actually, I don't even need the parentheses now because the exponent is 1 and everything's in the denominator. So there it is, right? That's our first partial with respect to x. Now let's see what it looks like if we differentiate with respect to y. So first partial with respect to y. So now we have at least one term in the top that has a y and the bottom that has a y. But then we have these terms that don't have a y at all. So let's see. Quotient rule again. When I differentiate 3x, right, with respect to y, because we're going to treat now x and z as constants, then the 3x is a constant, so its derivative is 0, and then bring down the minus. And then again, when I differentiate my e, I get the e, but again, I have to apply the chain rule. So now differentiating the inner part with respect to y means that x comes down, the derivative of y with respect to y is 1, so we end up multiplying by x. Right, so chain rule here, just as it is here, but you can see the difference in terms of what we end up multiplying by. That the derivative of the inner is different depending on what our variable of differentiation is, right? And then this part is still the same because we still have to take the derivative of the top times the bottom. So we have the sine of z plus y squared minus the top. So that's 3x minus e to the xy. Now when I multiply by the derivative of the bottom, because the bottom has a y, we're not going to have the nice simplification that we had before. So it's going to end up being a little bit messy. But this term doesn't have a y, so its partial derivative with respect to y is 0. This term gives me a 2y after differentiation. So I have 2y there, and then we still have the same over the denominator squared. So the sine of z plus y squared squared. Now, because of this term, right, unless I'm going to, and I'm not going to spend too much time with the algebra, right? But what I will just say is this. So you have 0, and then you have this negative e times the x. So I'll write this as negative x e to the xy times this quantity of the sine of z plus y squared. And then, yeah, there's not much we could do. I mean, you could certainly distribute this term. I'm just going to leave it factored, but I like to put the 2y in front, and then we have the 3x minus e to the xy, and then at the bottom, no need to FOIL anything out. I'm just going to keep it as the sine of z plus y squared squared. All right. So that's our partial with respect to y. And now, finally, let's do the partial with respect to z. So our partial with respect to z, and as you might expect, what we're going to do, we're going to treat x and y as constants. So treat x and y as constants. And this is what we have. So when the nice thing about this is there is only one term in this whole function that has a z. So lots of things are going to be 0. Let's see what it looks like. Right. Again, I'm going to use the quotient rule. There are other things you could do. You could turn this into a product rule by bringing up the entire denominator and raising it to the power -1. You could do that. But again, I just want to emphasize again the quotient rule. It's always good to practice the different rules. So when I take the derivative of the numerator with respect to z, there is no z. So we're going to have 0 times, and then I'll still put the bottom, but we know what's going to happen there. So sine of z plus y squared, and then minus the top. So that 3x minus e to the xy is there, and then times the derivative of the bottom. The derivative of the sine of z with respect to z is cosine of z, right? And then the derivative of y squared with respect to x. There is no z, I'm sorry, with respect to z, not x. So let's say this again. The partial derivative of y squared with respect to z is 0. So that's there. And then this is all over the denominator squared. So they all have the same denominator prior to simplifying. You know, like when you set up your quotient rule, you'll have this, but the numerators are, you know, dramatically different. So let's simplify this one. Right, and let's see, yep, so now this goes, but unlike our first partial with respect to x, we don't have another factor of the sine of z plus y squared. So basically what we have, and I'll keep things factored, I'm going to, so we have the negative of the quantity 3x minus e to the xy, and then times the cosine of z. I can drop the parentheses because that term is 0, and then this is all over the quantity sine of z plus y squared right? And there we go. So you could see, like, once we establish this level of comfort as far as treating certain variables as constants and remembering which variable we're differentiating with respect to, the process of partial differentiation is really just regular differentiation with more letters, right? It's like just a very rich alphabet soup of letters. You just have to know which letters go where and in what particular form. All right. So for this, yeah, so let's go ahead and wrap this video up, and then in the next video we'll talk about, okay, well, what's at least one interpretation of this partial derivative. So I will see you then.